This ECC memory controller works because it evaluates check bits. The clever bit here is repairing bit flips seamlessly. Inside server racks, cosmic radiation or thermal noise can flip a single charge within DRAM. If a standard memory controller reads corrupted charge, software receives bad data or crashes immediately. Server processors prevent crashes by integrating error-correcting hardware directly inside the silicon memory controller. This dedicated controller intercepts memory reads, repairing corrupted bits before operating system kernels see them. Initially, early computer engineers attempted to combat memory corruption by appending a single parity bit to every transferred byte or word of data. A standard parity generator works by counting the binary ones across a data word and setting the parity bit to guarantee an even total sum. If an energetic particle flips one bit during storage, the controller recalculates parity during readback and immediately detects that an unexpected error has occurred. However, simple parity logic can only report that a failure happened. It is incapable of identifying which specific bit position in the word was inverted. Because the controller cannot pin down the exact corrupted bit location, it cannot repair the word, leaving the operating system no choice but to crash. To solve this severe diagnostic limitation, memory system designers replaced basic parity with structured linear matrix codes that calculate multiple overlapping check bits. By assigning each check bit to monitor a carefully calculated subset of data bits, the memory controller generates a distinct error signature called a syndrome. When a single bit flips during storage, the calculated pattern of mismatched check bits creates a unique binary syndrome pointing directly to the broken index. With the exact bit coordinate pinpointed, the memory controller simply routes that bit through a hardware logic inverter, restoring its true binary value instantly. The newly restored data word is then passed directly to CPU registers, allowing demanding server applications to execute continuously without crashing or corrupting files. The bigger problem was handling multi-bit corruption, where two independent memory bits within the exact same word flip simultaneously due to severe interference. When two bits flip at the same time, standard single-error Hamming logic gets tricked into calculating a misleading syndrome value that points to a perfectly healthy bit. If the controller attempts to repair that erroneously identified bit position, it accidentally flips a good bit, introducing a third corrupted bit into the word. It appeared mathematically impossible to distinguish between a fixable single-bit flip and a dangerous double-bit failure without drastically expanding redundant memory check overhead. Adding excessive check bits to every transfer would heavily choke memory bus bandwidth and require huge silicon die area, making server processors far too expensive. Engineers masterfully solved this engineering dilemma by expanding the matrix logic into a SEC-DED structure, standing for single error correction and double error detection. This enhanced Hamming scheme adds a comprehensive overall parity bit that spans the entire combined width of data bits and individual check bits. In standard enterprise server hardware, 64 bits of user payload data are paired with 8 specialized check bits, creating a 72-bit word. During every memory write operation, high-speed logic gates inside the controller evaluate the incoming 64 data bits and calculate the 8 check bits in real time. The resulting 72-bit word is stored across physical DRAM chips, placing the payload data and redundant check information directly side by side. When the central processor requests a read, the memory controller retrieves all 72 bits from the DRAM modules in a single high-bandwidth burst. The memory controller immediately feeds the retrieved 64 data bits into internal silicon logic gates to calculate a fresh set of expected check bits. It then performs a bitwise exclusive OR operation between the stored check bits and the fresh check bits, producing an 8-bit syndrome result. If every single bit in the calculated syndrome evaluates to 0, the memory word has suffered 0 corruption during its time in storage. The controller immediately forwards the pristine 64-bit data payload straight into the CPU cache hierarchy, with virtually 0 added memory access latency. If the calculated syndrome is non-zero and overall parity confirms an odd number of error bits, the controller verifies that a single bit flip occurred. The numerical value of the 8-bit syndrome corresponds directly to the exact matrix column belonging to the corrupted data or check bit.
The memory controller immediately passes the target bit through an integrated XOR gate, restoring 0 to 1 or 1 to 0 before sending data onward. If the syndrome is non-zero but overall parity shows an even bit count, the controller accurately detects a severe double-bit memory failure. Because double-bit errors cannot be repaired safely, the controller refuses to guess, blocking bad data and raising a system exception to the processor. This controlled hardware halt prevents corrupted data from ever reaching application memory, writing bad records to database drives, or damaging file systems. Crucially, ECC hardware serves as one vital reliability layer in modern enterprise architecture, rather than a substitute for data backups or an absolute guarantee against corruption. Engineers design these high-reliability systems for long-term server rack deployment, never attempt to open, inspect, or service energized computer hardware components.
By embedding SEC-dead Hamming logic directly into silicon memory controllers, modern enterprise servers quietly correct millions of memory errors every single day. Transient bit flips caused by cosmic radiation or electrical noise are caught and repaired in nanoseconds, long before operating software or users ever notice. This elegant combination of linear matrix algebra and high-speed silicon logic transforms delicate electronic charges into a rock-solid foundation for cloud infrastructure. By mastering real-time error correction inside the hardware layer, server memory controllers ensure that complex computing tasks remain fast, stable, and remarkably reliable.